Hello, today I am looking at this Samsung microwave. It actually stopped working. It could no longer heat the food. So what I'm going to do is to pull apart the microwave and just recycle the parts, just to tear it down and have a look what's inside it. I'll also be showing you what's inside a microwave oven, looking at the high voltage section. It's what powers the entire system, and taking a closer look at the magnetron, the heart of it all. I've taken everything apart so you can see each component clearly. And yes, I've powered it up safely on a table just so you can see it work. Finally, I've created a schematic to do a deep dive and explain how everything works. Most people talk about the magnetron, which is the heart of a microwave. And that's the part that actually heats up the food. It generates the high power and focuses the electromagnetic waves into the food and cooks it. So rather than get into that though, I will just link to some videos I have found who've done quite a good job at explaining how the magnetron works, and they've pulled it apart and you can sort of see the insides. It's quite a magical little component. So I will just focus on stripping this apart and seeing what we can reuse. You know, we've got buttons in here, touch buttons here. We've got a nice display here. There's lights, motors to turn the table, all sorts of things. So it'll be quite interesting to see what we can get out of this. And just a note on how microwaves work at the very basic level, right? The magnetron shoots the waves out here and they bounce around inside here. And metal reflects the electromagnetic waves and they just stay in there to cook the food. On the screen door itself, you will notice a whole bunch of little holes. And that's just a metal screen with little holes in it. So the microwaves actually bounce back in and you can still see your food. And there's there's usually more than one switch here as well. So when you close this, you will see something like this for here and here. And these are like safety switches. You need more than one switch to make sure everything is working before the microwaves start being shot into the food. So yeah, there's a few safety mechanisms and things like that. So I'm going to just pull this apart and just reuse the parts. We've already bought a new microwave, couldn't wait. So yeah, no repairing for this one. I'm going to start pulling it apart. Just a note, when pulling apart a microwave, there's a lot of dangerous things in there. Dangerous voltages, dangerous capacitors, all sorts of things. So we need to be very careful about how we do that and to take care, right? This is the magnetron, or the magic happens. Here we have the capacitor. Once the transformer. We have a fan here, which cools down the magnetron, which I'll show you when I pull out. And we have a control panel over here, and a bunch of wire. And that's really it. There's not a lot to a microwave these days. So I'll pull out these parts and we'll see what we can do with them post. And just to see here, you know the switches here that are for the door in here. Two switches, safety. Push button to open the door here. Quite basic mechanical. This here goes into the magnetron to heat up the filament, which radiates the electrons into the magnetron chamber, which then generates the electric fields. Up here we have a sensor, a heat sensor by the looks of it. There's a light bulb here. Okay. This is the magnetron. Two big magnets here. I'm actually curious to pull the magnets out to see how strong they are relative to other magnets. It's been said from others that this particular pink part should be made out of aluminium dioxide versus beryllium, and beryllium is meant to be very poisonous. Aluminium dioxide is not. So anyway, you can be very careful with that either way, because we don't want that in a powdered form. So I will tape it up later when I get to pull this apart. Okay, one switch here. Here's the transformer. Lots of windings in this baby. Not sure what this is, but probably a diode. Here's the capacitor. Yeah, the specs are like 2100 volts AC and only 0.95 microfarads. Yeah, so we're talking a high voltage, low capacitance. Simple AC motor. Nice solid switches. Another one. Yeah, once this heats up, it basically disconnects these contacts and stops everything from working. Simple heat switch. You can see here, basically a little switch. So the main power came in to distribute some relays, little buzzer. So this goes to the panel switches. And there we have it. Interested to see what's under here and how it's done, but there's no physical buttons by the looks of it. It's just through this flexi cable. And here's the motor. You can see it's a geared motor because it's not in the center. It's 21 volts AC, 5 to 6 revolutions per minute, about 3 watts. Okay, so that's basically it, as a tin box with a few electronics to drive a few AC motors and Magnetron. Okay, just want to summarize what we got here. So we got a Magnetron, we got our transformer, high voltage transformer, we got our AC light, we have some mechanical switches, heat sensor switch. This is a high voltage diode, RG408. We have some input filtering through the mains, our high voltage capacitor, electric motor here, and the control panel for the whole thing. So even on here, some of the stuff we can recover, some of the parts. Yeah, because I have no use for the board itself, so I may pull that apart. Great. Next step will be to pull apart the magnetron and recover the magnets. Okay, I'm going to pull apart this section here. I started a little bit. It's quite tough. The way it's put together here is that this top sort of hooks into here with these prongs inside there, which means you really just got to pry this apart carefully. I can't stress how careful you need to be. We don't want to bang this insulator, which I've wrapped in tape. The internet, YouTube, seems to say most likely not beryllium, and so it shouldn't be poisonous, but some say it could be. So do this with extreme care, if you must do, if you're into this sort of thing. Okay, now that that hook's taken out, just do the same over here. Okay, should we just lift this up? Wow. All right. Oh, magnets. Well, they are strong. As I said, I will link to some videos about how the magnetron works. It's quite remarkable technology. It's quite a cool little mesh of wire. Also careful not to slip and gash your hand out. I think there's some wires under there, so I better not do that. I need to open it from the bottom. Okay, one step at a time. Okay, some luck for you. And this is what's inside. So we got a couple coils, bit of ferrite here. Just going to cut that. Hopefully this then can come off. All right. I will not be opening up the magnetron. There are other videos that have done that. No additional learning if I do it. And I just don't want to risk damaging this. All I want is this magnet. So we have one here. You can see if we can get this one off. Yeah. Okay, so we've got the magnet off. And now I'm going to just see if I can get under this metal. Always push away with the blade away from your hand. Okay, we're under it. There we go. Must have been a little bit of glue or something holding it down. And let's see. Bingo. It's also magnetic. Oh, don't do that. I did not realize that was that strong. Okay. All right, that's it. This is the magnetron. It's actually inside this cavity that the whole swirl of electrons are focused in a particular way that they then shoot out an electromagnetic energy through this antenna type function, which cooks your food. Originally, it was designed for radar and then costed down for microwaves. Before I show the video of this circuit running, it's actually what's inside the microwave, or what was inside the microwave. We have the control board here, we have the microwave oven transformer, we have the light, we have the cooling fan for the magnetron, we have the rotary table for the plate inside the microwave, we have the thermal sensor here, we have switches. One switch is here, another switch is here, and one runs behind here, which we cannot see. So the video will show this running, and I just want you to see that, you know, for example, here, 25 volts is tapped out of this coil to run this 25 volt AC rotary motor. And this particular switch, once the microwave starts, it connects the main power to enable all of the main electronics, the transformer, the light, the fan, etc. And once it finishes the timer, it disconnects the power, and so nothing is running through this. Okay? One thing to highlight is that this particular switch here, I'll show this in a schematic as well. Just to highlight, when this switch here is actually open while the power is on, it actually shorts the main and neutral power source, causing this fuse to actually blow. So it's some sort of safety mechanism, and I suppose they feel that if there's a short, then the whole thing just cuts out, nothing works. So let's run the video and you can see it running and basically all these things working together. After pulling apart the microwave, I thought it would be cool to show you how it was all wired up. I've created a schematic to illustrate the various stages from the power supply to the part that actually cooks your food. So here's where the power enters the microwave through the mains. Typically it's 240 volts, in America it may be 120 volts, and it immediately passes through a fuse for protection, and a filter circuit to reduce the noise from the microwave circuits from feeding back into the mains. Next, we have the control board, which acts like the brain of the microwave, ensuring that it does what it's supposed to do and when to do it. I've simplified this down to the very basics, showing only the critical voltage control switching components. All the timer, display, and button controls, etc. are not shown. One key function of the control board is that it ensures the oven only runs when the door is securely closed. Multiple door switches, here and here, serve as a fail-safe, preventing power from reaching the high voltage components unless everything is properly latched. So I will walk you through the behavior of each of these components. Firstly, I just want to say that, as a note, all of the switches are in the position as if the door is closed. So you can see by default the path is closed for current to flow once the control board enables these relays to pass through the current. Not shown here on the mains board is the mains power, which is actually always applied to power the clock and some sensor circuits, etc. By default, no power is passed through to the internal components until needed. And you can see that here where the neutral line is open by default. Okay, so there's no path through. Even this one comes through here, but it's open. So when the door is opened by pressing the lever on the front of the microwave, it opens this switch, and in doing so it detects that, right? And once it detects that, the control board will then switch on this relay, this one, which will then allow power through this connection. And as you can see, the only path is actually the light. So we open the door, the light switches on. Power through here doesn't actually get through because if the door is opened, this is also open, so no power passes through. So when the start button is pressed, once the door is closed, to cook the food, both of these relays actually switch on, connecting the power through to the light, the fan, and the rotary motor. So if you can see these two things being closed, this connection comes through here to power the light, the motor, and the fan, which go through here. Transformer you can see through this connection, right? So all of the power electronics then get powered. Just to point out that the light and the cooling fan are powered by 240 volts, okay, these two. But I found that the motor that rotates the plate is only powered at 25 volts, which is done by taking a tap out of the coil on the motor. So it taps out at 25 volts and powers the motor. It was rated at 21 volts AC, but they actually applied 25 volts across it. Looking at the temperature sensor, which is attached to the magnetron casing, it will break the mains power to the whole microwave, including the motherboard, if the magnetron overheats. It might have been actually better to shut down the high power circuitry and give some warning to the display, but the way it's done, everything shuts off and you're left wondering what happened. But they've done this, I suppose, as a safety measure. I just want to also point out to these two switches, this one and this one, which are connected to the door, which both break the electrical path if the door is opened. And that causes the high power circuits to shut down. So if the user is not bothered with pressing the stop button on the front panel and just chooses to open the door, this ensures that the microwaves don't come flying out the door. It just immediately cuts off the power. I want to highlight how this switch actually works. If for some reason this switch, this one here, fails and remains on when the door is opened, right, like something's gone wrong, or there is a failure in the motherboard to detect the door opening, maybe this one, or both maybe go bad, right? This switch here will actually short circuit the mains through this path. So if you can see here, this connection, Now, if this is opened, the live is now directly connected to the neutral, which would cause a short, and that would blow this fuse. So this would be considered a major failure and force the microwave to be serviced. Because once the fuse is blown, there's no way starting it unless you replace it. I actually tried this on the table where I opened this switch while it was on, and it blew the fuse on the input filter board. Next we have the high voltage generation. So at the core of the power delivery system is a heavy duty transformer. It steps up the 240 volt mains to over 2000 volts AC on its secondary side. The voltage then feeds into a special circuit made up of a high voltage diode and a capacitor, forming a half-wave voltage doubler, also known as a clamping circuit. So the capacitor charges during one half of the AC cycle, and during the next half, its stored charge adds to the incoming voltage, producing sharp, high voltage pulses of approximately 4000 volts DC. And I just want to highlight, you can see here that it's AC, but once it goes through the clamping circuit, it causes a 4000 volt DC. And DC because you can see in this little drawing here I put together, this is 0 volts here, and this is negative 4000. And what happens is, when the capacitor is initially not charged, you have this negative going 2000 volts. But once it is charged, the voltage goes to negative 4000 volts and continues as a sinusoid. It's considered DC because it doesn't cross the 0 line, right? So it stays in the negative half. It's negative because of the way the clamping circuit is done. It's a negative clamp. You can make positive clamps, but for the magnetron, we need a negative 4000 volts to accelerate the electrons. Now, I said it is DC, but it's actually what we call pulsating DC voltage. And you might wonder, why pulsate? Why not just have a fixed DC? Because it's not too hard to add in another diode and a capacitor to filter this to be nice, steady, solid 4000 volts. But it so turns out that microwaves are built with this pulsating voltage so that the magnetron doesn't overheat. If this was a constant 4000 volts non-stop, the magnetron would just overheat and then become inefficient and have all sorts of problems. So it's done this way so that extensive cooling systems are not required in a microwave, and that keeps it cheap. If we added more cooling systems and more electronics, it would get more expensive. So this ends up working out for a microwave. Now I'd like to talk about this 3 volts. So this 3 volts is tapped from the transformer, and it's done in such a way that it's very high current. So this 3 volts, which is relative across the cathode, right? Because this point here is actually negative 4000 volts relative to ground. But since this coil is isolated, right, there's actually only 3 volts across the cathode or the filament. And so when this 10 amps goes through the filament, it causes it to get really hot, causing thermionic radiation, which means the electrons are coming off this and shooting across towards the anode within this very strong electric field created by the negative 4000 volts. The last thing I would like to talk about regarding the electrical aspects of the circuit is the actual grounding of the anode of the magnetron, right? So the anode is that large metal block that forms most of the magnetron's body, the one with all the fins in it. So if you ground the anode, the whole exterior of this magnetron casing stays at 0 volts relative to Earth, right? And this is actually safer for people servicing the oven and easier to shield. You see, if the anode were at negative 4000 volts, so this area here connected to the negative 4000 volts instead, Any accidental contact or arc to the chassis or ground would be extremely dangerous. Yeah, easy to get electrocuted. So the cathode is actually small and centrally located, making it much easier to insulate and isolate that high voltage. So with the anode grounded, this coupling connects directly to the grounded waveguide without needing any extra high voltage isolation. So if you can imagine needing to put something around the magnetron, all of that casing, protecting that high voltage if it was present, would be quite difficult and even more expensive. So that just gives an idea why it is done this way within the microwave. Every design aspect and every way that this is set up is actually to cost down the microwave. You know, there are other ways of doing it, but this implementation really shows how efficiently things can be designed to keep costs down. So yeah, I think that's quite interesting regarding the way they did that. So that's it for this video. I really hope you enjoyed it and you got something from it. You can see here all of the different parts that you can pull from a microwave, which can be quite useful in different projects. I also hope you got something from the schematic walkthrough, really seeing how a microwave functions during its operation. The wiring is not that complicated, but there are some tricks that they've employed to keep it cheap, safe, and functional. So please drop any comments, like and subscribe. That would be awesome. I'd love to hear from you. And I look forward to catching you in the next video. Cheers.